This discovery is just the beginning. As more data pours in from the James Webb Space Telescope, astronomers expect to uncover even more anomalies and surprises hidden in the early chapters of cosmic history. The notion that the early universe was quiet and uneventful is quickly being replaced by a vision of rapid activity and unexpected complexity. Every observation from JWST seems to peel back another layer of cosmic mystery, revealing that the early universe may have been more dynamic and crowded with energetic processes than we ever dared to imagine. In light of this, scientists are rethinking the timelines they once believed to be solid. If bright, structured galaxies and faint energy signatures were already present within just a few 100 million years after the Big Bang, what else might have existed during this period? Could there be entire populations of exotic objects, perhaps massive stars, dense star clusters, or even early supermassive black holes, that we have yet to detect? These possibilities are pushing cosmologists to revise their models and explore alternative theories of cosmic evolution that allow for more rapid development in the universe's infancy. One emerging theory is that dark matter, the mysterious invisible substance thought to make up about 85% of the matter in the universe, may have played a more active role than previously believed. Traditionally, dark matter was considered a passive gravitational scaffold around which galaxies could form. But new data suggests that it may have triggered rapid collapses of gas into dense regions, accelerating the birth of stars and galaxies. If this is the case, the very structure of the universe could be intricately tied to the behavior of dark matter in ways we still don't fully comprehend. Another hypothesis gaining traction is that the first stars, known as population 3 stars, were far more massive and short-lived than stars that formed later. These stars would have burned intensely bright, lived only a few million years, and then exploded as supernovae, seeding their surroundings with heavy elements and triggering further rounds of star formation. While no population 3 star has ever been directly observed, the unusual brightness and chemical composition of early structures spotted by JWST may offer indirect evidence of their existence. It's also worth noting that the very method by which the James Webb Space Telescope observes the universe contributes to these groundbreaking revelations. Unlike the Hubble Space Telescope, which excels at observing the universe in visible and ultraviolet light, JWST specializes in infrared wavelengths. Infrared light has a longer wavelength, allowing it to pass through cosmic dust and revealing hidden regions of space. Moreover, because the universe is expanding, light from distant galaxies is redshifted, stretched into the infrared part of the spectrum, by the time it reaches us. JWST's ability to capture this faint, stretched light makes it an unparalleled tool for peering into the distant past. This unprecedented capability is allowing astronomers to perform what is essentially cosmic archaeology. By studying these ancient light signals, we're reconstructing the earliest epochs of our universe in a way that was never possible before. And as JWST continues its mission, it's expected to peer even further back in time, perhaps all the way to the very first light that ever existed. What we find could completely overturn our current understanding of the cosmos and spark a new era of discovery. But with these new discoveries come new puzzles. For instance, the structure spotted by JWST is not just bright, it appears to be chemically mature. This means that heavy elements like carbon, oxygen, and even iron are present in amounts that suggest multiple generations of stars had already lived and died. This is surprising because, according to current models, there simply wasn't enough time for this kind of stellar evolution to have taken place. How could such mature materials exist in such a young universe? One possibility is that our understanding of time and matter in the early universe is incomplete. Perhaps the early universe was not as homogeneous and slow-evolving as we assumed. Instead, certain pockets of space may have experienced accelerated development, driven by unknown factors such as variations in dark energy, interactions with exotic particles, or even phenomena beyond the standard model of physics. These ideas are speculative but increasingly necessary as observational data continues to outpace existing theories. In fact, some scientists are even revisiting alternative cosmological models. One such idea is the cosmic inflation theory, which proposes that the universe underwent a brief but rapid expansion immediately after the Big Bang. While this theory has strong support, the data from JWST could force revisions to the timeline or the nature of this inflationary period. Perhaps the inflation was more chaotic, creating uneven patches of spacetime where galaxies could form faster than others. Or maybe inflation ended in a way that seeded the universe with denser regions ripe for early star formation. Another radical idea under discussion is that we might be observing the effects of quantum gravity, a theoretical framework that attempts to merge quantum mechanics with general relativity. If quantum effects played a significant role in shaping the fabric of spacetime during the universe's earliest moments, it could explain some of the anomalies JWST is now revealing. While we are far from confirming such theories, the data is forcing the scientific community to think outside the box and explore all possibilities. Ultimately, what makes these findings so exciting is not just what they reveal, but what they suggest might still be out there. For every mystery JWST solves, it raises new questions. What if there are galaxies that formed even earlier than the ones we've seen? What if some structures are so faint or so different from our expectations that we've been missing them entirely? And what if, in our search for the first stars and galaxies, we stumble upon something even more fundamental, like evidence of the multiverse or signatures of a pre-Big Bang state? These questions may sound like science fiction, but they're increasingly becoming the domain of serious scientific inquiry. With each new observation, JWST is expanding the boundaries of what we consider possible. And in doing so, it's not just teaching us about the past, it's shaping the future of astrophysics, cosmology, and our place in the universe. By probing deeper into the dark ages, the James Webb Space Telescope, JWST, may uncover new insights about the conditions that ultimately led to the birth of the very first stars and galaxies in the universe. The cosmic dark ages, a time before the formation of stars, has long been a period of great interest and mystery in astrophysics. Could there have been other, previously unknown sources of radiation during this era? Might exotic forms of physics, such as the decaying of dark matter, be responsible for the unexpected emissions observed during this time? These are just some of the profound questions that JWST aims to address. However, one thing is certain: the cosmic dark ages were not as dark or empty as we once thought. There was far more activity than earlier models predicted. Let's delve into why we are now seeing what we do, especially considering that scientists once predicted we would never be able to observe such phenomena. One of the greatest cosmic mysteries came to light in the mid-20th century, when early infrared and radio observations detected a faint, persistent glow coming from deep space. This glow, unlike the well-studied cosmic microwave background, CMB, which is the afterglow of the Big Bang itself, didn't match any known sources of radiation. While the CMB is an expected remnant from the birth of the universe, this glow was different. It didn't come from galaxies, quasars, or nebulae, but instead appeared as a diffuse, all-encompassing emission stretching across vast regions of the cosmos. This was particularly perplexing because it seemed to originate from a time before the first stars had formed, during an era when the universe was thought to be completely dark. At first, astronomers speculated that this signal might be an observational artifact or stray light from known cosmic structures. However, as technology advanced and instruments became more refined, the signal persisted. The European Space Agency's Infrared Space Observatory, followed by NASA's Spitzer Space Telescope, confirmed this anomaly. Despite this, neither observatory could pinpoint the source of the emissions. The discovery of the extragalactic background light and the cosmic infrared background added further complexity, as these diffuse emissions contained components that didn't match the expected contributions from galaxies alone. In some regions of the sky, there was an excess of this glow, sparking the theory that something else, something unseen, was responsible for illuminating the early universe. Over the years, numerous hypotheses emerged to explain this puzzling glow. One of the most intriguing theories proposed that the early universe contained massive clouds of primordial gas that collapsed into compact, star-like structures but never fully ignited. These objects, often referred to as dark stars, or population 3 remnants, could have emitted faint radiation through processes such as gravitational heating or exotic particle interactions. Some physicists even speculated that this unexplained light could be linked to the decay or annihilation of dark matter particles in deep space. Dark matter, which is invisible to conventional observation, could potentially produce faint electromagnetic emissions under the right conditions. If this theory proves true, it would represent the first indirect detection of dark matter. Another fascinating possibility was that primordial black holes, which are believed to have formed shortly after the Big Bang, could have slowly accreted gas, producing weak but persistent emissions long before the first stars were born. Unlike the supermassive black holes that we observe in modern galaxies, these early black holes would have been much smaller and scattered throughout the cosmos. As they accreted gas, they would have generated diffuse radiation that could account for the mysterious glow. Some astronomers also speculated that small, dense clumps of gas, precursors to the first galaxies, could have emitted weak Lyman alpha radiation due to early ionization effects. This, too, would suggest that the dark ages of the universe were not as dark as once believed and that light-producing interactions occurred much earlier than expected. Despite these theories, however, direct observational proof remained elusive. The light was there, but its exact source remained a mystery. That is, until the JWST entered the scene, bringing new clarity to this long-standing enigma. JWST's revolutionary capabilities allowed it to peer deeper into the cosmos than ever before, and its findings suggest that the mysterious glow may be the result of primordial gas clouds, dense regions of hydrogen and helium collapsing under their own gravity. These clouds, long before the formation of stars, were able to emit weak radiation through molecular cooling and turbulence. This process, known as gravitational heating, produced a diffuse glow that filled the early universe, much like a foggy haze. The difference between these early gas clouds and conventional star formation is that these clouds did not undergo nuclear fusion, but instead released energy via molecular cooling processes. This explanation accounts for why the glow appeared as an all-encompassing background emission rather than coming from localized sources. Furthermore, JWST has provided indirect evidence supporting the theory of early black hole formation. Some of the mysterious light observed in the early universe may be linked to small-scale accretion activity in primordial black holes. This finding supports the notion that these enigmatic objects existed much earlier than previously thought and may have played a significant role in the early development of the universe. If proven, this would drastically reshape our understanding of black hole evolution, suggesting that they played a crucial role in shaping the cosmos long before galaxies began to take shape. Another remarkable discovery made by the JWST was the detection of two ancient galaxies that, by all known cosmological models, should not exist. These galaxies, among the most distant ever observed, date back to a time when the universe was less than 400 million years old. At this point, the universe was still in its infancy, and galaxies were expected to be small, irregular, and chaotic structures. However, what JWST uncovered was something entirely unexpected. Two galaxies that were surprisingly massive, well-formed, and mature, despite the fact that they existed in such an early stage of cosmic history. These galaxies, identified as Glass Z12 and Sierra 1749, were formed within the first few hundred million years after the Big Bang. According to the widely accepted lambda cold dark matter model of cosmology, galaxies at this stage should have been small, clumpy, and just beginning to form their first stars. Instead, these galaxies were unexpectedly large, with well-organized structures and features more typical of galaxies that are billions of years older. To put this discovery into perspective, these galaxies appear to contain tens to hundreds of billions of stars, something that, by current cosmological theories, should have taken over a billion years to achieve. This observation challenges our understanding of galaxy formation and evolution and raises new questions about the processes that govern the early universe. The findings from the JWST regarding early galaxies have completely shattered what we thought we knew about cosmic history. These newly discovered galaxies defy our understanding of how the universe should have evolved during its formative years. According to our current theoretical models, galaxies that formed less than 400 million years after the Big Bang should have been small, irregular, and in the process of forming their first stars. Instead, the JWST revealed massive, well-structured galaxies that seem to have skipped the slow, gradual evolution expected at that stage. These ancient galaxies, named Glass Z12 and Sierra 1749, showed an astonishing level of maturity, suggesting a level of organization that should have taken billions of years to achieve. But here they were, looking almost as developed as galaxies that are much older. To understand why this is so significant, we have to look at the theoretical timeline of galaxy formation. According to the standard cosmological model, galaxies should grow gradually, accumulating gas and merging with smaller structures over hundreds of millions of years. However, these newly discovered galaxies appear to have bypassed this slow process altogether. They are not the chaotic, irregular clusters we expected. Instead, they are well-formed, with dense, mature structures and an abundance of stars, something that should take over a billion years to develop. Adding to the mystery is the presence of heavy elements in these galaxies. Elements heavier than hydrogen and helium are typically formed in the cores of massive stars and spread through supernova explosions. For these elements to be present so early in the universe, there would need to have been multiple generations of stars living and dying within just a few hundred million years. This level of evolution is far beyond what our models predict. The discovery of these galaxies raises profound questions about our current understanding of the universe's early years. If these galaxies really exist as we see them, it would require major revisions to our understanding of how the universe evolved. One possibility is that our models of cosmic expansion are incomplete and that the early universe expanded much more rapidly than we thought. Another possibility is that star formation was far more efficient than previously assumed. Perhaps the most radical implication is that our entire understanding of galaxy formation needs to be revised. If galaxies can form much earlier and more quickly than we expected, we might have to rethink fundamental aspects of dark matter, gravity, and the structure of the cosmos itself. Some researchers are even considering whether we need to modify our theories of gravity or include new physics to explain these surprising findings. But the surprises don't stop there. The JWST has also detected something that raises even more eyebrows: unusually strong Lyman alpha emissions coming from galaxies at the edge of the universe. These emissions, which occur when young stars ionize surrounding hydrogen gas, typically provide key insights into a galaxy's age, composition, and star formation rate. However, during the epoch of cosmic reionization, roughly 400 million to 1 billion years after the Big Bang, this light should have been absorbed by the thick clouds of neutral hydrogen filling the universe. Yet, the JWST detected these emissions in galaxies that should have been hidden by the neutral hydrogen. How is this possible? One possibility is that these early galaxies were undergoing violent mergers. Galactic mergers cause intense gravitational interactions that compress gas clouds, triggering rapid bursts of star formation. These starbursts produce vast amounts of ionizing radiation, which would excite the surrounding hydrogen gas and produce Lyman alpha emissions. In essence, these early galaxies may have been much more dynamic and active than previously thought, growing explosively through mergers and accumulating mass at astonishing rates. While galactic mergers and star formation can explain the production of Lyman alpha emissions, they don't fully account for why this light was able to travel freely through space. The intergalactic medium, which was mostly opaque to ultraviolet radiation during this period, should have absorbed the Lyman alpha photons before they reached the JWST's instruments. Yet somehow the light was able to escape. This suggests that something else was at play. It could be that cosmic reionization didn't happen in a smooth, uniform process, but instead took place in localized, patchy regions around the first galaxies. These regions, created by intense starbursts and mergers, could have cleared away the surrounding neutral hydrogen, allowing Lyman alpha photons to pass through more easily. Alternatively, there may have been less neutral hydrogen in certain regions of the early universe than we had predicted, which would have weakened the absorption of light. If this is the case, it could mean that cosmic reionization occurred more quickly and on a more localized scale than we thought, challenging our previous assumptions. These findings raise the possibility that unknown physical processes could have been at work, influencing the way light propagated through the early universe. They also suggest that galaxies were much more chaotic and active than we initially imagined, evolving rapidly through mergers, bursts of star formation, and dynamic interactions. But that's not the end of the story. The JWST has also revealed something even more astonishing: the presence of a supermassive black hole at the heart of a galaxy that existed less than 500 million years after the Big Bang. According to current models of black hole formation, such a massive object shouldn't have existed at this early stage in the universe. Black holes are thought to grow gradually by accreting surrounding matter over time, but this supermassive black hole appears to have formed too quickly to fit within these models. This black hole is not just large, it's truly massive, likely containing over 1 billion times the mass of the Sun. In the modern universe, supermassive black holes are found at the centers of large galaxies like our own Milky Way, but they form over billions of years through the slow accumulation of matter. Finding one so soon after the Big Bang raises serious questions about the mechanisms behind their formation. Current models suggest that black holes begin as stellar mass objects, with only a few times the mass of the Sun, and grow over time. But this supermassive black hole would have had less than 500 million years to grow to such a size, far too short a time for a stellar mass black hole to reach this magnitude. This discovery prompts an urgent question: did black holes in the early universe form through an entirely different process? Some astrophysicists are now considering the possibility of direct collapse black holes. This theory proposes that vast clouds of primordial gas could have collapsed directly into black holes without first forming stars. Unlike typical black hole formation, which begins with a supernova explosion, direct collapse black holes could have started with masses tens or even hundreds of thousands of times that of the Sun, allowing them to grow rapidly into supermassive black holes. If this process was common in the early universe, it would fundamentally change our understanding of black hole formation and cosmic structure. Alternatively, it's possible that early black holes grew far more efficiently than we thought, accreting matter at a much faster rate than current models allow. If the Eddington limit, the maximum rate at which a black hole can accrete material, was somehow exceeded, it could explain how black holes grew so quickly in the early universe. One possibility for these extreme black hole growth rates is through a process known as super-Eddington accretion. In this scenario, gas and matter flow into a black hole at extraordinary speeds and densities, enabling rapid and explosive growth. If early black holes were able to sustain this kind of extreme feeding frenzy, they could have ballooned to supermassive sizes in a fraction of the time that we thought possible. However, this theory challenges a long-standing principle in astrophysics and suggests the need for an unknown mechanism that allows black holes to grow much more efficiently than they do today. This raises the intriguing possibility that some black holes may have formed through different processes than we previously imagined. A more speculative, yet equally fascinating idea is that some black holes might have been born directly from the Big Bang. These hypothetical objects are known as primordial black holes, and they could have formed from extreme density fluctuations in the earliest moments of the universe. If these primordial black holes existed, they might have started out much more massive than stellar mass black holes, allowing them to grow into supermassive black holes at extraordinary speeds. The existence of primordial black holes would be revolutionary, potentially changing our understanding of the early universe, dark matter, and even the fundamental laws of physics. If primordial black holes were common, they could explain some of the unsolved mysteries we encounter today, such as the unexpectedly high number of massive black holes detected by the James Webb Space Telescope, JWST. However, there is currently no direct evidence to support the existence of these primordial black holes. In the years ahead, JWST will continue to examine more early galaxies to determine how widespread these massive black holes were. Additionally, upcoming telescopes such as the Nancy Grace Roman Space Telescope and the Extremely Large Telescope will provide more precise data on black hole formation during the universe's first few 100 million years. For now, the discovery of a supermassive black hole so soon after the Big Bang is forcing scientists to rethink the very foundations of how galaxies and black holes form. Whether this leads to a refined version of current models or sparks a groundbreaking new understanding of the cosmos, one thing is clear: the universe is far more mysterious and complex than we ever imagined. And speaking of mysteries, there are even more of them to explore. For decades, cosmology has been guided by a well-structured timeline that included the Big Bang, the Dark Ages, the formation of the first stars, and the emergence of galaxies several 100 million years later. However, the discoveries made by JWST have thrown this timeline into disarray. The telescope has uncovered massive, well-formed galaxies that existed far earlier than anyone thought possible. This finding has ignited a heated debate among astrophysicists, some of whom now question whether our understanding of galaxy formation, cosmic evolution, and even the age of the universe itself is fundamentally flawed. Could it be that the universe is actually older than we've estimated, or is there something extraordinary and unknown that occurred shortly after the Big Bang that allowed galaxies to form at such unprecedented speeds? If JWST's findings continue to hold up under scrutiny, the entire framework of how we think the cosmos unfolded after the Big Bang might need a radical revision. According to the standard model of cosmology, the first galaxies should have taken several 100 million years to form after the Big Bang. The early universe was a hot, dense plasma, which first had to cool, allowing atoms to form during a phase called recombination. This led to the Dark Ages, a period before the first stars ignited. After a few 100 million years, the earliest galaxies were expected to emerge, slowly assembling through gravitational attraction. However, JWST has detected massive, well-formed galaxies at redshifts of 12 to 16, corresponding to a time just 200 to 300 million years after the Big Bang, far earlier than our models predicted. These galaxies should not exist. There simply wasn't enough time for gas and dust to clump together under gravity and form stars in such a short period. Additionally, the early universe was still filled with neutral hydrogen, which should have suppressed the formation of galaxies. And even more astonishing, the rate of star formation needed to produce such massive galaxies exceeds what we currently understand about physics. Some astrophysicists propose that galaxies formed much more efficiently than previously thought, but this alone doesn't fully explain the data. The issue isn't just that galaxies formed early, but that they appear far too mature, bright, and massive for their age. If these galaxies are indeed as old as they appear, it forces us to rethink our models of galaxy formation. We must also entertain the possibility that the universe itself is older than previously believed, or that something unknown accelerated galaxy formation after the Big Bang. This is radically different from what we knew before. Our current understanding of the age of the universe is based on measurements of cosmic expansion using the Hubble constant and observations of the cosmic microwave background. These calculations suggest that the universe is approximately 13.8 billion years old. However, JWST's findings are prompting some scientists to reconsider this number. If galaxies were already forming less than 250 million years after the Big Bang, it could mean that either the expansion rate of the universe was miscalculated or that the universe is actually older than we think. Increasing the age of the universe by a few hundred million years might not seem drastic, but it would fundamentally reshape our understanding of cosmic history. There are other possibilities as well. Perhaps the Hubble constant has been miscalculated, suggesting the universe is a billion years older than previously believed. Or maybe an unknown phase of accelerated cosmic evolution condensed galaxy formation into a much shorter time span. We also have to be open to the idea that the standard Big Bang model might be incomplete. While these ideas remain controversial, JWST's groundbreaking discoveries have reignited debates about the accuracy of our cosmic clock. One of the more radical ideas is that our Big Bang model itself may be incomplete. Some physicists suggest the universe could have experienced a period of pre-Big Bang existence, where structures began forming in a previous cycle of the universe. The concept of a cyclic universe, where the cosmos undergoes repeated phases of expansion and contraction, has been explored in various theories, including loop quantum cosmology. Whatever the case may be, the James Webb Space Telescope has significantly expanded the boundaries of observational astronomy, making discoveries that challenge the very foundations of modern cosmology. With its unparalleled ability to peer into the depths of cosmic history, JWST has revealed galaxies that appear too mature, too massive, and too structured for their position in the early universe. These findings have sent shockwaves through the scientific community, and while they remain at a crucial crossroads, awaiting spectroscopic confirmation of their redshifts, they offer the potential to revolutionize our understanding of the cosmos. If these redshifts are confirmed, indicating these galaxies genuinely existed within the first few hundred million years after the Big Bang, cosmology as we know it could be rewritten. The future of our understanding will depend on additional data from upcoming telescopes, such as the Nancy Grace Roman Space Telescope and next-generation ground-based observatories. Until then, the scientific community waits eagerly, knowing that the next few years could redefine our understanding of the universe in ways we never imagined.